Hello everyone. This is third lecture, which is probability amplitude from Feynman lectures, volume 3, chapter 3. Okay. In this chapter, we are going to understand about law of combining amplitude. So, first of all, I want to introduce you to some new notations. So, there are Dirac notations, which are like phi equals to this bracket. This gives information of particle arrives at x, and this gives particle leaves from s. So we always read it from right to left. So particle leave from s means particle is leaving from here, and particle arrives at x means it arrives at this point. Okay, and this phi gives the amplitude. And when we take its absolute square, we get the probability. So uh, please remember, always read it from right to left to track initial and final point. Okay, so amplitude is a single number which is complex in nature, means it has a phase. So what is this phase? So let's say we have amplitude which is in the form r into e raised to power iota theta, which if you know is a complex number where theta is this phase. So probability can be given for a situation if it starts from S and end at X by absolute square of it. Okay, I think this must be clear till now. Now, new notation for a second general principle when particle can reach a given state by two possible routes. So there are two amplitudes. Now, uh, two paths. Why we said two paths? So one possibility is that this particle from S can go from hole 1 to X, or it can take path from hole to this from S to this hole 2, then this X. So when particle reach a given state by two possible routes, then total amplitude can be given by phi 1 plus phi 2, and this its probability can be given by absolute square of it. So this is the probability. So total amplitude in Dirac notation can be given by this. This start from S and end at X. Now, in terms of hole, it travels from hole 1, this one, and this one travels from hole 2. So this is the Dirac notations. Now, if this is also Dirac notations, which we already have this p square absolute square. Okay, there is a mistake here. No mistake. Okay, it's okay. So roughness involved. We could split each hole into pieces with a certain amplitude that the electron goes to the top or bottom of hole and so on. We will suppose that hole is small enough so that we don't have to worry about this detail. Okay. So third general principle, when particle goes by some particular route, the amplitude for that, let's say amplitude to go from S to X by hole 1 can be given by this Dirac notation. We are going to read it from right to left. So particle starts from S, then go to hole 1, then from hole 1 it go to X. Okay. In same way, amplitude to go from S to X by hole 2 can be given by it starts from S, then go to hole 2, then from hole 2 it go to X. So for amplitude to go from S to X by hole 2, can be understand here we are going from S to hole 2, okay, this part, then hole 2 to X, this part, okay. When both holes are open, we just add them up, okay, which is our this first second general principle. So how to write much more complicated paths? Let's say now I have inserted uh, another wall with three holes, okay. Here we have two holes, then we have three holes A, B, C. So how many probabilities can be there? So first possibility is that particle can go from hole 1, then to hole A, then to X. Okay, it might go from hole 1 to hole B, then X, or hole 1 to hole C to X, or it can follow these paths: hole 2 to hole A, then X, hole 2 to hole B, then X, hole 2 to hole C, then X. Okay, so for this complicated path, you can just check it out. Uh, so for this condition, okay, for this condition, uh, we are going from source to 1, then 1 to hole A, then hole A to X. Okay. Now for the second condition, source to 1, hole 1 to B, then B to X. You can check it if you want to check. This is the generalized form of it. So what information we need to go from one place to another? We need amplitude to get from one place to another. Uh, if we are going from R2 to R1, this is the amplitude for it. Okay, where R12 is difference of R2 minus R1 vectors. And this P is momentum, which is related to energy E by relativistic equation in this form, or in a non-relativistic case equation, this is the form. Okay, and now uh, here you see these time terms, t terms, t1 and t2. This depends on both r and t. Since for now we assume that the source emits particle with a given energy, so we will not need to worry about uh, time. Okay, so compare between classical and quantum wave. So to understand the wave, what I am talking about, we have to first remove the uh, picture of wave that we have in our mind, which is the classical one. Okay, so aspect is like what is waving here. So in classical sense, uh, density and pressure of the gas molecule is waving. This is direct physical measurable quantity. But in quantum wave, nothing material is waving. It is a complex valued field of probability amplitude. It is math description of system state. Okay. So what does amplitude means here? Large amplitude means large sound. Okay. So amplitude is here directly proportional to pressure change. Okay. Here we are considering this sound wave for classical. Now here amplitude give probability of finding particle at a given point in space time. Now is directly measurable? Yes, we can directly measure this pressure using microphone or etc. whatever we want to find. But in quantum wave, no, only probabilities, square of probability amplitude can be measured. So the math says it's wave, but it's a probability wave, not a stuff wave in case of quantum wave. Okay, you can again check it that the math says it's wave, but it's a probability wave, not a stuff wave. Okay. So some important points to be noticed: quantum wave is impossible to visualize as a simple wave in our 3D space. You can't plot a single wave that has 6 dimensions. Okay, we need higher dimension space called configuration space. So for one particle, configuration space is 3 dimensional. For two particles, it is 6 dimensional. For n particle, it is 3n dimensional. So this shatters the idea of physical wavy substance in 3D space. Okay. Now, how do we build wave function for this complex multi-dimensional space in non-identical case? So provided that two particles do not interact. So let's say for particle 1, this is the amplitude, and for particle 2, this is the amplitude. So amplitude that both will happen together. So if they happen together, we just multiply them, these amplitudes. So in quantum mechanics, you don't need to know the entire history of particle. You only need the amplitude for it to be in various possible starting states for next part of the journey. Okay. Now the two slit interference pattern. So they here phi1 stands for amplitude that electron will arrive at x by way of hole 1. So for this whole one, we have an amplitude in terms of phi1, which you can see. We are going to read it from right to left. The particle goes from source to then whole one, then whole one to x. Okay. Same way, phi2 stands for amplitudes that electron will arrive uh, at x by whole 2. So this is the amplitude here. You can check if you want to check that we are going from source to whole 2, then whole 2 to x. So these are amplitudes to go through two holes and arrive at x if there is no light. Okay, if there is light, what is the amplitude? So D1 detects photons behind hole 1 and D2 detects photons behind hole 2. This is the modified version. So this D1 and D2 are now detecting the photons which are emitted by this light source. So 1s is the amplitude to reach from source to hole 1. Okay, this uh, Dirac notation here. So from source to 1 up to here we get the amplitude. Now let's say A is the amplitude of photon scattered by electron passing through hole 1 and detected at D1. So if our particle is detected by this photon and it is scattered to this D1, we can give the amplitude by A. So now for next case, to this Dirac notation, uh, x1 amplitude to reach from hole 1 to x. So from here to here, we use this amplitude. Now the amplitude that electron goes from S to X by hole 1 and scatters a photon into D1 is given by multiplication of this, which I already told you that if two particles do not interact with each other, then amplitude that both will happen together is given by multiplication of it. So these are amplitudes to go through two holes and arrive at X if there is no, uh, sorry, where I was. So the amplitude that electron goes from S to X by whole one and scatters a photon is given by this. And there will be some amplitude that electron going from slit 2 will scatter a photon into D1. Amplitude that an electron goes by 2 and scatter a photon into D1 is given by this. Now amplitude to find electron at X and photon in D1 is the sum of two terms. So this is the sum. So in same way, amplitude to find electron at X and photon in D2 is also is the sum of two terms, which is like this. It might get confused. You can stop and understand it from here. So we don't have correct math formula for all the factors that go into calculation. We can easily calculate probability for various situations. So case one is the ideal experiment. Let's say if B is 0, which is the way we want to design the apparatus. Now probability P is just a square and phi 1 absolute square. So a square is the probability that electron going through slit 1 actually detected by this D1, and phi 1 square is the probability we do get if only slit 1 was open and we were not seeing the electron. Now case 2, if photon's wavelength is very long, then scattering behind the hole 2 into D1 may be just about the same as for hole 1, although there may be some phases involved in A and B. Now, if the wavelength is long, let's say two phases are equal in sense of A equals to B. So we can conclude that this is the result that photon detection is ineffective and we get the interference pattern. Case 3 is if using short wavelength that B is not equals to 0 but less than A. So this is the result of weakened interference. Faint phases will be on the screen and partial detection of the information regarding the path taken by the electron. Now, here is the summary for situation case 1A, which path information gives us the complete information about which path it had taken in our case 1 situation. Now, what it looks like the single slit diffraction. Here you can see, and probability can be given by P equals to A square phi 1 square. Now, case 2B. uh, path information here is none. We don't know about the path information. Acha, what it looks like? It looks like full double slit interference, as you can see here and here also, which means probability formula is P equals to A square, absolute square of phi 1 plus phi 2. And case 3, path information is partial, not complete. So it looks like weakened interference, faint fringes, and formula is this, which we already have seen, and this is the graph for it. Now, total probability that electron arrives at X after get detected by detectors can be given by the sum of these two probabilities. So here I'm saying it probability because we have done the this square of these amplitudes. Okay. Now the common errors, suppose that you only want the amplitude that electron arrives at X, then you just do this A phi 1 plus B phi 2 plus B phi 1 plus B phi 2, which is wrong, distinguishability test. Find out which path happened. So here is a little trick if you want, if you are interested. If no path are indistinguishable, yeah, if you can say path are indistinguishable, you can just add the amplitudes. Okay. If path are distinguishable, add probabilities. So here, path are distinguishable, so we just add up the probabilities. Okay. To scattering from a crystal. Now, I think this video is going long, so I will explain it in another video. That's it for today. And hope so if you are confused, having doubt, or my method is bit creepy, you can comment it. I'll try to improve my videos in next session. Thank you so much for being with me.